So when you do the Laplace transform, a lot of times you end up with this Laplace transformed variable, capital Y of S. And capital Y of S is often in the form of some numerator of S over some denominator of S. That's what N and D stand for in this particular case. And to figure out what we're going to do, and furthermore, the denominator is usually of the form of some polynomial in S, in which case it could possibly be factored into multiple binomials. So denominator, let's say the denominator can be expressed in the term, in the form of S plus A1 times quantity S plus A2 times the quantity dot 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 all the way up to S plus A sub n. So that's usually what you see, some sort of form of the denominator that looks like this. Okay, and these A's, or the minus A's, the minus AI's, are the zeros of the denominator, which is the same thing as the poles of Y of S. So the zeros of the denominator are the poles of the Y of S. So let's say your denominator is some polynomial in S, like, you know, S to the fourth plus AS cubed plus whatever, right? And you look at that polynomial and you say, what are the zeros of that polynomial? When you figure out what the zeros of the polynomial are, you can factor the polynomial into a bunch of binomials. So what we're looking at right now is the case in which all zeros of D of S are real and distinct. So that's this case that we're looking at now. And if they're all real and distinct, then that's the case in which you can factor them into these binomials. And that's the typical case that we'll be dealing with in here. But there are two other cases that we'll talk about in a sec. Okay, so if it turns out that if you can express the denominator like this as a bunch of product of a bunch of binomials, then you can do what's known as partial fraction expansion. So partial fraction expansion will look like this. You'll have some constant C1 over S plus A1 plus some constant C2 over S plus A2 dot 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 plus some constant Cn over S plus A sub n. So that's what's known as partial fraction expansion. And maybe you've already seen that in like Calc 2 when you're solving certain integrals. The same idea, right? So now what we're ending up with is a sum, instead of a fraction where the denominator is a product of binomials. Now the whole thing is a sum of 1 over those binomials, or a linear combination, I should say. The reason why we're doing this is that now if I can express my capital Y of S in this form, then it's in a form that I can do what's known as an inverse Laplace transform. So this function right here, or this term here, can be inverse Laplace transformed into something in the time domain, and that's what makes it useful to me. Okay, so if I scroll back up to the first page of these notes, and I look at a small snippet of the different things that we can inverse Laplace transform, this here is one of them, where 1 over S plus some constant inverse Laplace transforms back to e to the negative of that constant times t. Now I've said this once in here before, and I'm going to say it again. I'm not a super big fan of memorization, but some things you should memorize. And this relationship, where if you have e to the minus at, Laplace transforms into 1 over s plus a, and inverse Laplace transforms back, this is something you definitely should memorize. We're going to see this over and over again. 1 over s plus a inverse Laplace transforms back to something that we want, or we can express easily, which is an exponential in time. Before I move on further on partial fraction expansion, if I scroll down to the very, very, very last page of this topic, we have a more comprehensive table of the different Laplace transforms you might encounter. That's the last page. And one of them is right here, which is the one I just mentioned. And we will eventually, in the next couple days, get to these two as well. Another one that's super important to memorize. So I wouldn't necessarily memorize this one. Don't necessarily memorize the sine and cosine one, but definitely memorize the e to the minus at, and definitely memorize this one, the step input. Those two I would definitely memorize because they keep popping up over and over again. And the reason why the step input pops up a lot is because a lot of times in this class, the way that the problems will run is you'll say, you'll have some unit operation that's at steady state, and then at time t equals 0, something suddenly changes from one value to another. That would be a step input. And so you'll need to do a little Laplace transform of the step input, which would give you some constant over s. Okay, I do want to get into the example problem, so let me get back to the partial fraction expansion, and then we'll get to the example problem. Okay, where were we? Okay, so let's say that we have our partial fraction expansion going here. How do I solve for what the values of these coefficients are, C1, C2, etc.? The first thing you do is we are going to multiply by the denominator. Another way of saying that is we're going to clear the denominator. So this partial fraction expansion is a constant over s plus a1 plus another constant over s plus a2. We want to get rid of all the s plus a's in the denominator here. So I'm going to multiply by this whole denominator, which is the product of all the binomials. Multiply both sides of the equation by that. And what we end up with is we end up with our numerator, n of s by itself on the left-hand side, is equal to, on the right-hand side, C1 times the quantity s plus a2 times the quantity s plus a3 dot 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 times the quantity s plus an. That was C1 plus C2 times the quantity s plus a1 times s plus a3 dot 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 all the way up to s plus a sub n plus C3 times the quantity, etc., etc. So what clearing the denominator did is it gives me a coefficient times a bunch of binomials plus a second coefficient times a bunch of binomials, etc. And if you look at the way these binomials shake out, the first term here, where you have C1, that term lacks, or there is no s plus a1. There's no s plus a1 binomial in that term, because when I multiply by all the binomials, the s plus a1 canceled out here. So that first term doesn't contain the s plus a1. Furthermore, the second term, in the same way, does not contain s plus a2. The third term does not contain s plus a3, etc. So we're going to make use of that fact. We're going to substitute s equals to negative a1. Because this equation has to hold no matter what the value of s is. No matter what the value of s is, this equation has to be true. And so I can put in any value of s, and the equation still has to be true. So I'm going to pick certain values of s that's going to make the equation easier to deal with. So if I plug in s equals to negative a1, then my equation becomes n of s equals negative a1 is equal to c1 times negative a1 plus a2 times the quantity negative a1 plus a3 times the quantity negative a1, oops, let me do a dot 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 instead, dot 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 times the quantity negative a1 plus an. That's the first term, and that's the only term. That's the only term that's left, because every other term here has an s plus a1, and so every other term becomes 0. So if I substitute in the right value of a, then I isolate just c1. And then use algebra to solve for c1. Right? You just have c1 times all this on the right-hand side. You just divide all of these over to the left-hand side and get c1. When I say divide all of these values of a1 and a2, etc., they're just numbers, right? 3, 4, 2.5, whatever they are, you just multiply them all out and divide them to the other side, and you solve for c1, right? So then we have c1. Yay! We'd have to do the same thing for c2, right? So for c2, to find c2, we substitute s equals to negative a2. Same thing. And so now we have, on the left-hand side, n evaluated at s equals to negative a2, and that's equal to c2 on the right-hand side times the quantity negative a2 plus a1 times the quantity negative a2 plus a3 dot 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 all the way up to times the quantity negative a2 plus a sub n. And that term is the only term left, because that's the only term that lacked s plus a2. And so on and so forth. We could go on about this for days, but the pattern there is the same, right? So for every term, you figure out which s plus a is not in that term, and then when you substitute that negative a in there, that's the only term that remains left over, right? So that's the way in which you would solve for these coefficients, and that's how you deal with the partial fraction expansion when you have individual real poles.